And now we're down to solving this circuit. What I want to do now is put in the component values and solve this specific circuit. Let me move the screen up again. We'll leave the list of steps up there so we can see them. Let's go to work on this equation now. We have a little bit of algebra and we can plug in values where we need to. We can plug in 15 volts for V1. And for R1, we can plug in 4,000 ohms. We can put in for V2. V2 is still unknown. And that's divided by 4K. In this expression here, we still have V2 unknown over 2K. And IS, let's put IS over on the other side. IS was 3 milliamps. Let's just keep working at this now. V2 times 1 over 4K plus 1 over 2K equals 3 milliamps. Oh, get my minus signs right. Minus sign over here. Let's bring the constant term over to this side. So this is 15 volts divided by 4K. And continuing over here, we have minus V2. Let's combine those two resistor terms. So it's going to be 1 plus 2 over 4K equals 3 milliamps, and 15 volts divided by 4K is 3.75 minus 3.75 milliamps. Moving on, minus V2 equals minus 0.75 milliamps times 4K over 3. Let's get rid of the two minus signs. We don't need those anymore. And V2 equals 1 volt. That's good. We solved it. We solved for our two voltages. We have one here and we have one over here. And we can check off the last step. So that's our first application of the node voltage method. I want to show you one more thing that is a powerful part of this technique. Let me quickly sketch the schematic again. So this was our schematic, and we assign node voltages. We assign node voltages here, V1 and V2, and we made this our reference node. And one of the things we did not do as part of the node voltage method, we did not use KVL to write equations around these loops. And one of the features of the node voltage method is that the KVL equations, because we're using node voltages, the KVL equations are automatically satisfied. And I'll show you why. I want to put one more label on here, which is the element voltage. We'll call this VR1. That's the element voltage across here. The element voltage here is just V2. So in this case, for R2, V2 is the element voltage and the node voltage at the same time. VR1 is an element voltage. And now we're going to write KVL starting from this point and going around the loop in this direction. And what we have is, let's get all our labels on here. The loop voltages, we start with a rise of plus Vs, then we take away VR1, and then we take away V2, and that equals 0. So that would be the KVL equation for this this circuit. Now I'm going to plug in, using node voltages, I'm going to write VR1. So I get plus Vs minus VR1 is node voltage V1 minus node voltage V2. V1 minus V2 minus V2 equals 0. And we'll just do one more substitution. I forgot, Vs and V1 are the same voltage. So this is actually V1 minus V2 minus V2 equals 0. And if we look at this equation, that goes, plus V2 minus V2. This equation is automatically true if we write Kirchhoff's current law in terms of node voltages. That always turns out to be the case. That's why we don't bother to do it. We know it's going to be true. So that's a nice feature of the node voltage method. It's a really efficient way to write equations. You only write KCL equations. And this is such a good method, in fact, that circuit simulators, like you may come across a circuit simulator called SPICE. Almost every circuit simulator uses this node voltage method to do its computations.